Okay, so what we are looking at in the last class is various different reduction strategies for lambda calculus, and we had looked at, I mean, we went down this deep rabbit hole, right? So we said, okay, there's this nice thing called reduction, and I told you there are several different kinds of reductions. You have full beta reduction, you have normal order reduction, and then you have call by name reduction, and we saw a specialization called call by need, and we saw call by value. So so the idea is that all of these reductions exist for very pragmatic reasons, right? So some are very theoretical, like full beta reduction is non-deterministic, and normal order is reducing under lambdas, which is sort of not what real languages do. And this call by need and call by value are practically motivated, right? So they sort of capture the essence of two different paradigms of functional programming. One is so basically the evaluation strategy, right? So the one is lazy evaluation. Haskell is the sort of epitomizes lazy evaluation in functional programming. I mean, it's sort of the other popular functional programming language, which tends to be more popular than OCaml. I mean, when people think about functional programming, they sort of, if they know a particular functional programming language, it might usually be Haskell or Scala, right? But Haskell sort of is Puritan in terms of the sort of functional programming style it espouses, and certainly Haskell has weird semantics for a lot of the things, including evaluation. And the call by need is what it does, and it mirrors lazy evaluation done in Haskell. And call by value is what the evaluation strategy that all the languages, including like every language that you probably programmed with, right? So all the C++ languages, Python, everything, and OCaml also use call by value. So call by need is lazy evaluation. Call by value is strict evaluation, right? So that's what we saw in the last class. So we also studied this notion of beta equivalence, right? So if I give you two lambda terms, I can ask whether these two terms are beta equivalent. And the way you do it is, if you reduce it, would you reach the same term, right? Modulo alpha equivalence, right? So, so this is a nice equivalence property that you can have for lambda calculus. The higher level question you might ask is like, I give you two programs, OCaml programs, right? Does the two OCaml programs that I give you, the functions I might give you, behave the same way, right? If I want to capture the behavior of the two functions, you might want an argument that is similar to beta equivalence, right? And beta equivalence is works very well for lambda calculus because it lacks many of the features that OCaml has. But the question you want to ask is whether beta equivalence is the best notion of equality between lambda terms, right? And it turns out it isn't, because it misses out one corner case, and that corner case is presented here, right? Consider this this statement, right? So it says lambda x dot sin x is beta equivalent to just the function sine, right? If you sort of imagine, so first thing you want to ask is whether this equivalence holds. It doesn't, right? Because this is already a beta redux, you cannot reduce it anymore. Assume you have this sine function, right? Primitive sine function that is exposed. So according to the definition of beta equivalence, these are not the same, right? These are not alpha equivalent, certainly, because there are extra lambda abstractions here, right? And which is not here. And they are not beta equivalent because you cannot go from one to the other by either reduction or saying they are alpha equivalent. But we know that these two functions are the same, right? All the function here does is whatever argument that you pass here, it simply calls that function, right? So sorry, it simply applies sign to that value. So intuitively, this should be equivalent to this definition, right? But beta equivalence and alpha equivalence doesn't capture this particular equivalence. So in particular, right? So just to put it formally, for all, if I say for all m, right? Once you add this m, these two terms are certainly beta equivalent, because you can reduce it, right? At this point, this is a redex, so you can reduce, you can throw m here, and you will get sin m, and which is sin m, which is the same term, they are alpha equivalent term. So this equivalence holds, but this doesn't, right? So this is sort of unfortunate. This is like, oh, we've done all of this hard work, but there is this small thing on the side which you have to worry about. And really, what we have is another form of equivalence. This is very, very simple, right? This is not going to be very complicated. And all it says is that if you have a lambda x, mx, we call that eta equivalent to m, right? If x is not a free variable of m. So the premise is important, because if you have an x here, right, which is used in m, then the meaning changes, right? So this will be, let's say m is just x, in which case this is lambda x applied to x, right? But this would be just variable x, where x is a free variable. So that particular this particular premise is quite important. Under this premise, if you sort of say x is not a free variable of m, then this equivalence intuitively holds, right? And this is what we call as eta equivalence. And it turns out that beta eta equivalence captures the equality of lambda terms quite nicely, right? If you want to say, I have two lambda terms, are these equivalent, right? Are the behavior of, or the semantics, is the semantics of these two lambda terms equivalent? The best equality that you can sort of hope for is beta eta equivalence, right? Beta eta equivalence just says that it is either beta equivalent or eta equivalent, right? So um, okay, and we also have this idea of, just like beta reduction, we have eta reduction, right? And again, this is directly using the intuition, right? So if you have a lambda x, mx, then you can eta reduce it to m. You're just throwing away this abstraction that is sitting for no reason, right? So you're just throwing away that to get m. Actually, we've done that in the example, right? When we first looked at higher order functions. So we had this example of shirt color, where we said, okay, I'm mapping this list.map function. Sorry, I'm using list.map over a list. And the function that I'm mapping is, for every element, get the shirt color of X, right? And I said, okay, this is equivalent to just applying shirt color directly, right? So, and this is more idiomatic. We often don't write it explicitly like this, because we are adding this anonymous function for no reason, right? This color takes whatever the element kind does and returns a shirt color, and this does the same thing. So eta equivalence is very intuitive. You've actually done it previously. Okay, so that's eta reduction. And that concludes the lecture on the semantics of lambda expressions, right? So we've seen a lot of different things. I can directly sort of go to the next lecture and sort of do a recap. Oops. Yeah, so what we've seen is um, we saw beta reductions mainly, right? We just focused a lot on beta reductions. We saw different reduction strategies. We also saw what normal forms are, what is beta normal form. So you reduce something to a lambda term which cannot be beta reduced anymore. And the last thing that we saw is extensionality, right? So this extensionality just means eta equivalence and eta reductions. So that sort of captures the semantics of untyped lambda calculus, right? Entirely. And as I hinted in the first lecture, right? So lambda calculus is equivalent in expressive power to Turing machines. So you should be able to encode all the things that you do in a high-level language just using lambda calculus that we've seen so far, right? Which only has, say, anonymous functions, right? And has functional applications and variables, but they are sort of falling out of the fact that you have functions, right? And in this lecture, what we will see is we will look at how to encode higher level programming features. Like we'll see Booleans, right? It's good enough because, there is a question, sir, can you provide an intuition of how it was proved that eta equivalence is good enough? We don't have a proof. I just told you it is good enough, right? So you have to take my word for it. It's just I think it's hard to quantify what a good enough is, right? So we are sort of looking at program equivalence, and the idea of so it is both defined and given by this very definition of beta eta equivalence, right? How do you define two terms are equivalent? We say beta, right? We observe that there is this corner case that is not sufficient, but we don't have a completeness argument. So, so that's the answer to your question. So getting back, right? So the thing that lambda calculus has is okay. So Srisha, is there a eta equivalent version of lambda xx? No, right? So there is no eta equivalent because that's an identity function. In eta equivalence, it is always the case that you have a lambda x, fx, right? Some f applied to x, and all you're doing is saying, I will just take this as x. Sorry, f. I'll remove the useless abstraction that is sitting around it. So you cannot have a eta equivalent version of lambda xx, but you can always. Yeah, it is a function, but eta equivalence can be applied when there is an application, right, in the body. You can get a eta equivalent term of this, right? I can sort of wrap this lambda xx term on the outside with the, so you're asking what is the, give me an, if I just sort of take your question as, I have a term which is lambda xx, right? And I want to get another term which is eta equivalent to this term. I can say this, right? I'm just adding a new layer. So these two are eta equivalent, right? This y is useless. Yeah, but you cannot make this smaller anymore. This is the actual function, right? This is like m, right? And what I have here is which is equivalent to, oops, I don't know why this is getting bigger, but this is equivalent to, so you can go from this to this using eta reduction, right? But you can't make this m smaller anymore. Okay, so I'll sort of get back to this lecture. So okay, so the thing that we have in lambda calculus is we have a single value, right? The value is the function definition, right? So the anonymous function is the only value that we have. But real languages have a lot of other things going on, right? It has Booleans, it has floating point numbers, it has arithmetic, it has algebraic data types, right? In OCaml, we have the ability to define algebraic data types like lists and trees and so on. We have record types, we have tuples and triples and whatnot. So if I tell you, right, so you can encode all of these using Lambda calculus, you have to ask me, show us an example, right? Show how to do all of this. This lecture is all about showing you how to encode higher level features, right? Including booleans, arithmetic pairs. We will also encode recursion, right? You have this ability to write recursive functions in OCaml. It turns out that with untyped lambda calculus, recursion naturally falls out. So the way to, so one word of warning about this lecture is it will look very much like puzzles, right? So this is going to be a little mind bending. Um, it is unlikely that you will learn everything, the way how encoding works, just in this lecture, right? When I explain it, it might not be easily picked up by you, because the reason is not that this stuff is hard. This is just like if you're sufficiently smart, you can come up with these encodings, right? And these encodings are a long, um, they have a long tradition of knowledge, right? So no one person came up with all of this encoding just in one day. So it's sort of, and there is no easy recipe that you can follow. I can't tell you, okay, if you want to do XYZ, um, you have to follow this recipe. So the way this lecture is going to be organized is we are going to look at a lot of examples, right? And you can sort of look at that example and maybe extend it a little bit further. But um, I won't ask you, say, encode records using lambda calculus, right? I'm not going to ask you questions like that. This is just an exploration of the expressive power of lambda calculus. Okay. So yeah, I think I mentioned all of this um, in the first slide. We also encode predicate logic, right? So this is what we meant. So we can encode any computation that we want if we are sufficiently clever, right? So I'm not going to force you to come up with an encoding of something completely new on the fly on the exam, right? So I'm not going to do that. So okay, so with that, let me clear the output. Restart and clear output. Okay, so again, I'm going to bring in the evaluators so that we can interactively explore these encodings, right? So I'm using unit.ml that loads up the definitions. I'm going to use a bunch of aliases, right, which are short form for expressing the expressions and parsing and so on. So I'm going to use the function name p for parsing a lambda string into a lambda AST. I'm going to use var, that just stands for the constructor var. So for application, I'm going to use notation where it takes a list of things, right? So and then applies from left to right. You will see examples as I explain it. I'm going to use lam for the constructor lam, right? It takes a x and an e, and it's just constructing this lambda. And I have an evaluation, and the evaluation order that I choose is normal order evaluation. So the thing to remember about normal order evaluation is um, it reduces under lambdas, right? This is important um, for the making sense of all of the encodings here, right? So whenever I call eval, all it's doing is it's evaluating in terms of normal order reduction. Okay. So here are some examples. So I bring in all that function. So p of lambda xx parses that into so let me make it smaller. So parses that into lambda x var x, right? And var x is just the ASD var x. I have a short form for application that can apply a list of lambda terms, right? So you can sort of imagine this to be just a short form for writing something like XYZ, right? So this is the term that I'm writing. So I use so this is interpreted as x applied to y applied to z, right? And that is what you have here, x applied to y, and the result of that applied to z. So writing as lists Yeah, you can. What is the notation? Where is? Oh, this one. Ah, okay. Good question. I'll finish this. So lam xy is just lambda xy. So this is I don't know whether we saw infix functions. We did see infix functions a little bit, right? When I write something like this is a int or int or int, right? This is just integer addition, but I can use this as a function as well, right? This function definition is just a it's a by using these brackets, right? I'm defining an infix function, so that you can use it like 5 plus 6, which is 11, but you can also use it just like a function, right? 5 6, right, which is also 11. So you can ask, okay, what is the operator this doing? I'm using this in infix position, right? But it's actually a function, and all that function does is takes a value, takes a function, and then applies this function to this value, right? Um, so it's like it's the same as rev apply x f fx. Okay, so that's the entire definition of that. I'm using, instead of rev apply, I'm using the name like this, right? So, and this is just a handy pipe operator. So if you programmed in Unix, right, we use this pipe operator to pipe results through. And it turns out that this comes in very handy. So S is some input value that I pipe to this function, which produces some output value, which I pipe to this function. So what am I doing here? I'm taking a string, right? And I'm piping this to evaluation. Actually, S is a lambda expression, right? So which I pass to this evaluator, which produces an AST for me. I want to print it in a nice fashion. So I'm converting that to a string here, right? So you can do, for example, let me give you one example and then I'll sort of stop. So you can do suck, right? And this gives me 2. And you can keep piping this, right? It gives me 3 and so on. Does that make sense, Satak? Yes, no? Okay. Again, this is not magic, right? This is just a function definition that I told you. It's an infix function that takes an argument and then takes the function and applies that function on the argument and returns the value. We won't use this often. I just happen to use it for no reason. Okay. So we have these helper definitions. Okay. So with that, we will sort of go into our first encoding. So we want to define Booleans now. First thing we want to do is define Booleans. So what do Booleans provide you, right? Booleans have two values, right? A Boolean value could be true or false. And you have some operators over the Boolean, right? You have if then else, which checks whether something is true or false. And based on that, takes another branch. You can have Boolean operators on Booleans, right? And or not, and all of that. So we will try to encode all this, right? So we want a definition of the Boolean constants, right? True and false. And then we want functions that operate over these constants, okay? But in Lambda calculus, we only have function abstractions, right? We can only use function abstractions. So in order to encode what a Boolean true or false value is, we will use functions, right? Here is the definition of true and false. Okay, so it might seem quite strange, but all that I say a true value is it's a function, right? That takes two arguments, true and a false, and then returns the first argument, right? So observe that in lambda calculus, everything is a function, right? So we sort of place this higher level meanings on top. When I say something is a true and a false, and it returns true. All I'm doing here is I'm defining a function that takes two arguments and returns the first argument, right? And for false, I'm saying that is also a function that takes two arguments, true and a t and a f, and then returns the second argument, right? That's the entire definition of true and false. You can ask, okay, I don't understand this. What is the point of using this definition? Actually, in order to understand why the definition is structured this way, we have to look at the functions that operate on them, right? The only things that can manipulate these constants are the functions, right? So now let's define a first function, right? And what is this function? It's going to work just like if then else, right? Test, if given a true and two branches, V and W, whatever needs to happen for V and W, if it is true, it is going to do whatever V is going to do. So by that, if you take this expression test, right, the function that we are going to define, this true, which is the value that we've defined here, two other lambda terms, V and W. If you beta reduce this whole thing, it will reduce to V, the first argument here. Now this term, test, false, the constant false here, VW gives, if you beta reduce it, gives you the second term, W, right? This is all it is doing. So here is the actual definition of test function, right? So the thing to notice is test takes three arguments, right? Test takes a true, a Boolean value, a term for the left-hand side, the term for the true branch, a term for the false branch. So test is going to be a function that takes three arguments, lmn, right? And the thing that is quite important here is we know that the first argument is going to be a Boolean value, right? And what is a Boolean value? A Boolean value is a function that takes two arguments and returns either the first or the second based on whether it is true or false, right? So the first one is a Boolean value, but we know because of the encoding that is a function. So we simply apply L to M and N. So the idea here, I'm trying to repeat the same thing, but the idea here is that if this L is true, right, and this L will be true, and I pass M and an N, because it is true function is going to return the first argument, it is just going to return M. If L is false, right, this will be false, and false is a function that just returns the second argument. So it is going to return N. Right? And that's the entire definition of the test function, right? It doesn't matter what it prints, right? So that is just a expression. So let's look at how this works, right? So if you apply test true VW, it has to return V. So it is going to do the true branch. So let's see whether that works, right? So I'm applying test true, right? And two variables V and W. This could be arbitrarily complicated expression because this is just a lambda expression. For simplicity, I'm writing down expressions this way, and I evaluate that expression. Okay. So first thing to notice is it is working correctly, right? So when I evaluate test true VW, it reduces to V. That is the specification that we describe here, right? It reduces to V. And you can see that the final result is V. And how did it actually work? So this is just an expansion of all of this, right? So test is this function which takes three arguments, applies for the first argument to the second one and the third one, right? True is just lambda TF returns T and then VW. So we are doing normal order reduction. So we reduce the leftmost thing first, right? So the true value gets substituted for L. So the L value gets substituted with the true value, right? And then we have V and W, which gets substituted for M and N, right? Stepwise, and you get this particular definition. which is true applied to V and W. And what does true do? True just returns the first argument, right? It ignores the second one, and that's why you get V. So here is a definition of what you will use, right? I could have renamed this as if then else. So if then else is a function that takes a boolean and then does the first true if the value of boolean is true and false if the value passed is false. I'll pause here because this is going to be the structure in which we are going to look at all of the encodings, right? Let's make sure at least we understand this particular encoding. You should have questions, right? So, or you might understand it completely. If you have questions, now is your time to ask. No questions on this. Okay. Then let's level up, right? Okay. Sir, so we can return functions, right? Yeah. Everything is a higher order function here. Yes, we can return functions. This could be arbitrarily complex, right? This could be a function as well. This could be instead of variable, it could be a lambda as well. Let me try to lam x bar x, right? So this is identity function lambda xx. So we return xx. This is exactly how OCaml operates, isn't it? You're asking a really good question, right? So is this exactly how OCaml operates? Yes and no. The semantics is the same, right? The semantics is exactly the same. So we have some extra syntax on top. In OCaml, I can write a function, right? So which is let test be boolean VW, which would be something like if then V else W. This function behaves the same way as whatever we do here, right? But this is not how OCaml implements this function internally. That is not how it is compiled, right? This is actually compiled to something very efficient, right? Just like how C would be compiled to x86 code, this is compiled to x86 in OCaml. But that's the point, right? We can understand the semantics of how OCaml works without having to tell you how this function is compiled. I have a different language in order to tell you how this works. And that's the point of studying lambda calculus. Good question. Okay, so structure is the same. Yeah, so we are writing OCaml here. So you can write so one thing that is different is this is untyped, right? So so let me try a different thing. I'm just trying something different. So this, okay, so this works in lambda calculus, right? But this particular function, if you encode directly in OCaml, will not work because in OCaml we have the static semantics as well, right? The semantics says that the type of the left and the right hand side branches must have to match. This is an identity function, right? And this is a function that takes two arguments and then returns the first argument. The types of these functions will be different. So this is a alpha to alpha function. This is alpha to beta to alpha function. So OCaml will not let you will not accept this function. But modulo that, yes, it's the same. That's a I'm sort of answering a different question to the one that you are probably asking. But does that give you more information? Okay. You said test takes 3 arguments, but it is actually taking 1 argument at a time, thrice. Yeah, just like OCaml. Yes. Yeah, I'm sort of using these terms loosely, right? because taking a function taking 3 arguments is the same as a function taking 1 argument, returning a function, taking the second argument, returning a function, which takes the third argument, returns something, just like OCaml. So when I say it takes 3 arguments, it's just um, it's far fewer words than actually explaining what is going on, but the intention is the same. Is that okay? Is there a notion of efficiency complexity in lambda calculus, or you can think about efficiency and complexity in lambda calculus, right? In terms of how many, say, applications you have to do. So if you sort of give a cost of 1 for each application, right? There might be different ways in which you can reduce it, so you can come up with the cost semantics, and this is what people do. Yeah, so yeah, you can do cost analysis on lambda calculus. We won't do it here. Okay, so I think I've answered a few questions. Any more questions? Okay, so I will continue. Okay, so here is the here is false, right? So the same example where instead of true I apply false, the result should be W for this one, right? So if I run this, I get W. You have the evaluation here, but the evaluation you can sort of, we know how beta reduction works at this point, right? So it's quite easy to follow what's going on. So I would leave it to you, right? Sometimes if there is anything interesting, I will explain it. Otherwise, the steps are defined here, and the reduction that we use is normal order reduction. So you just follow it along and you will understand what's going on. Okay. So it turns out that false itself is a function, right? So all test is doing is it's taking a function at 2 arguments and then applying this function to the both arguments. And in fact, test false VW is equivalent to false VW. You sort of stare at this, right? So this is test false VW. It evaluates to beta reduces to false VW. So actually, test is not adding any value at all in our exploration. So we will not consider test anymore. Wherever you want to say test false VW, you can just say false VW because both are the same thing. So false VW just returns the second argument, right? So false VW just returns W. So we are sort of because our constants are actually functions, so we can do this here. We don't have this separate notion of what a constant is. The value false is actually a function, so we can happily do this. Okay, so that's the true and false definition. Now we want to do more things, right? We want to perform logical operations and or and not and so on. So here is and, right? What does and do? True and false. If both are true, then return true. Otherwise, return false, right? And the way, so okay. So what is? Let's first establish what the signature of and function should be, right? And takes 2 arguments, right? It takes a boolean 1, boolean 2, and then returns a boolean. So here is the definition of and operator, right? And takes 2 functions. And takes 2 boolean values, a B and a C, right? And we know that every boolean is also a function, right? So you can directly, in order to test the value of the boolean, you just apply that function. So the way to read this is, if B is true, then the result is whatever C is. If C is true, then the result is true. Otherwise, it is false. If B is false, right, which means the second the value will be returned. So you just return false directly, right? So sort of look at this as if B is true, then the result of and is whatever the result of C is. If B is false, then we just return false. Okay. And similarly, what is R? R has the same signature, right? A boolean to boolean to boolean. So it takes two booleans and then returns a boolean. If one of the values is true, then you return true. So the way we do it again is it's a function that takes two boolean values, right? If B is true, then the result of OR is true. If B is false, then it is whatever the value of C is. If C is true, then it's true. Otherwise, it is false. So not think about negation. Negation is a function that takes one boolean, right, and returns another boolean, which is the negation of the value that is passed, right? So it is a lambda that takes it's a lambda, right? That takes an argument b, and the way to read this is if b is true, then the result is false. If b is false, then the result is true. So this is the encoding of not, and we have all the logical operators, even few of the logical operators defined here. Right? Any questions on this? Again, these are like puzzles, right? I'm sort of constructing these intricate puzzles that just work out. So here is the definition of and, or, and not. I'm using underscore here just so that this doesn't and, or, and not are reserved keywords, right? So I don't want to, yeah. So if you do and, it highlights that as a keyword. So that's why I'm using an underscore. The definition here is the same as the one here written out explicitly. Okay. And is boolean C false apply to true, and is boolean C false apply to true. I don't understand the question, Deepesh. And is C and false apply to true. So okay, so I don't understand the question. So you can actually play. Okay, true is also a function. Yes, true is also a function. Yeah. True is also, everything is a function. So we don't have anything else in lambda calculus. So the way you sort of look at this is it's a boolean. So we know that the structure of a boolean is that it takes two arguments and then returns one of them based on whether it is true or false, right? So that's why we are applying it to two arguments here. Yeah, so you can play around with the implementation, right? You can actually ask all of the questions that you have by interacting with this notebook and then playing around with it. Let's look at a few things, right? I want to speed up a little bit. So and or not is defined. Again, this is just an encoding of what I'm doing here. For example, I'm defining lambda b applied to false true, right? B applied to false true, right? So the rest of the things are the same. Again, this is not important. It's just the AST that is being printed. But what is important is whether the operators actually work well, right? What is the result of and true false? It should be false, right? So you can evaluate this. The thing that you get here, right, is a lambda which has the same structure. It's alpha equivalent to the false definition that we had earlier, right? So for example, this is false, right? So that's false. And this is alpha equivalent. The result of evaluation is alpha equivalent to false, right? So we are actually performing computation which is yielding us false as a result. So that's the way you have to read it, right? So this is yielding us false as a result. You can sort of look at this as a proof that true and false is false, right? So because we are actually evaluating this to false by not assuming anything about how the thing operates underneath. Everything is defined just through lambda calculus, right? Okay, and you can also encode higher level operators, right? Um, so we can encode logical implication using the standard formulation, right? It's not P or Q. And then here is a theorem, right? The theorem says that for all A, B, if A and B holds, then A holds, right? This is like this is obvious, right? So let's so the way we will prove this on paper, right? So we will actually use our you can use a truth table, for example, right? So or you use um, the standard definitions of how these things work and then prove it, right? So you actually reduce it to true eventually. So just like doing that, we can use lambda calculus to do the proof, right? So here is implication. All it says is um, so implication takes two arguments, right? It is, you can imagine this to be a function that is applied over a p and a q. So it takes p and a q as an argument, and the definition is not p or q, right? So or is on the outside, so there is an application or on negation of p and q. So we are directly encoding what implies this using lambda calculus, right? And I've sort of encoded theorem one as also as a function. So what is theorem one? Theorem one says for all AB. So I've encoded that as a lambda A, lambda B, right? I'm saying um, implication of A and B is A, right? So A and B implies A is what I've written down here, right? So okay, I've written that down. It expands to a large thing, that's fine. I've just written down the function, right? I've defined the implication. I've defined the theorem one statement. How do you prove this? By pen and paper, you can prove it by truth tables, right? And here we can prove it by case analysis. So there are four cases, right? A can be true, false. B can be true or false. In all of those cases, this theorem should be true, right? Whatever that evaluates to should be true. So here is the way to do it, right? So so there are four cases for A and B. So true, 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 false, false, true, false, false. All of these should evaluate to true, which means that the theorem holds, right? So here is the evaluation that evaluates to true. Theorem one true, false evaluates to true. Theorem one false, true evaluates to true. Theorem one false, false evaluates to true. So by case analysis on A and B, we've shown that this theorem holds, right? Without using any of the usual mechanisms, right? We are not constructing truth tables. We are not working through, like we are not using our logical reasoning to say, okay, implication is encoded in a way that it is not P or Q, so we can expand it. We are not using any of that, right? We are actually using lambda calculus as a way to prove this particular theorem just by evaluation. This is a different way of, so just to give you a hint, right? There is a field called program verification, in particular computer aided program verification, where the idea is that instead of doing proofs on paper, we will use proof assistants, which are just software programs which help you drive the proof, right? They are not going to automatically give you the proof. They sort of help you sort of say, okay, if you want to prove this, prove it by case analysis. So you have to show that each of these cases hold. Or you have to tell the proof assistant that you want to prove this by case analysis. And once you tell that you want to prove by case analysis, the computer knows what to do, right? These are Boolean values. So there are two values here, two values here. It has to evaluate to true for all of the cases. So we sort of encoded a very small theorem prover using lambda calculus here, right? We are doing it manually, but this is the principle by which all of these computerized theorem provers are actually implemented. They're doing something very similar to this underneath. Okay, so that, and hence proved. We've proved all of the cases, so the theorem holds. let's do this quick quiz and stop, right? So what is the lambda calculus encoding for exclusive OR X and Y? So what does exclusive OR do? If both are the same, then it is false. If X and Y are different, then it is true, right? So one of these is the correct answer. Um, can you guess which one it is? These two are just Boolean values, right? X and Y. Yeah, good. So third is the answer, right? Why? Because if X is true, right, then go and check if Y is true. If Y is true, then return false, right? If Y is false, it is true because we are in the true branch of X. Similarly, if X is false, if Y is true, then this whole thing returns true. If Y is false, it is false, right? So that's the reason why this is 3. So you might expect questions like this, right? So it's just I'm not going to ask you to design Booleans, right? But I might ask you to say, okay, what is the lambda calculus encoding for NAND, right? So, and I'll give you 4 options and you have to pick one. That's the level of questions I expect in the final exam. Yeah, okay. So, okay, I'll stop here and we can continue the rest of the things on Monday. This lecture is a bit long. We'll slowly go through it. But the idea is that you're going to see a lot of stuff in this lecture, which are going to be sort of mind-bending, right? It is better to take it as it is, right? So um, don't try to understand how something came about, right? Try to understand what it is. That is a better way of understanding this lecture. Okay. So I'll stop here and then we'll continue on Monday. Thank you.
Hello.
Yeah.
Sir, can you hear me?
Yeah, I can.
Sir, I had a few doubts that I came across while solving the assignment. So, should I ask you right now, or
You
ask
can
you
ask.
on Slack?
I think if it is something that you can ask in public, then sure.
Okay. So, sir, we had the fifth question in the assignment, in which we had to bucket the elements in the
Yeah.
list. So, the issue was that I wanted to iterate a list inside a list, right? So, do you
Yeah.
have any pointers on how I can go about that?
You can use a fold inside a fold, right? So that's totally fine. So does that make sense?
Fold inside of fold, right?
Yeah.
So can I use a match, a nested match?
Yeah. You can use a nested match, but if you really want like 2 for loops, right? 2
Yes.
folds is what you really want.
Okay.
Um,
So, in a way that fold is an analog of for loop in imperative
yeah.
programming.
Yeah. So think about fold as just as a for loop, right? So it might look weird, a little bit weird, but I think using that is the most natural way of doing this.
Okay. Okay, sir. And so the other question was that we have this if true then do something and else do something else.
Yeah,
We have this kind of if then else expression. So
yeah,
in imperative programming we have this concept of that if true then do a certain block of instructions and if false then
yeah,
do something else. So
yeah,
can we execute a
yeah.
certain set of instructions if it is true? Otherwise,
So the expressions could be complicated, right? So if true, then I can do print string hello, right? And print string world, right? Else unit. Yeah, I need. Yeah, so this, I mean, it's not printing, but I don't know why it's. But do you see what I'm doing here?
okay. So essentially, I have this.
You can use semicolon, right? So you can just write it like this. It'll just look imperative, right? So,
Okay. Okay, sir. And so last doubt was that let's say I want to create a function which takes
uh-huh,
some integer value. It's an
uh-huh,
integer, right? It
Okay.
doesn't take 3.0, it takes 3, and I
Okay.
want to add 1.5 to it and then return it. So how can I create such a function?
Okay. So there are two functions called int of float of int.
Okay, so I'll have to convert
Yeah.
from
So you
float.
have to explicitly convert because um, implicit conversion is not a thing that we allow in
True.
OCaml.
Yes, sir. Okay. 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 Thank you, sir.
Yeah. Okay. Any other questions regarding assignment?
No, sir.
Okay. So I'm hanging around. So if others have any questions, now is the time to ask.
Thank you, sir.
Yeah. Sure. Okay. Okay. So if there are no other questions, you can always ask me on Slack. I'll be there. Thank you very much. Bye bye.